Imagine standing on a bridge so high above the ground that if you accidentally dropped your phone, it would take nearly 10 seconds to reach the river below. 10 seconds. Long enough to panic, regret every life decision you've ever made, and wonder if gravity somehow forgot about your phone. Welcome to the Beipanjiang Bridge in southwest China, a structure so extreme that it redefined what engineers believed was possible. Rising 565 meters above the Beipan River, this bridge is taller than the Eiffel Tower and remains one of the highest bridges ever built. But what makes this bridge truly remarkable isn't its height. It's the fact that, for decades, experts believed a bridge here could never be built at all. Today, we're diving deep into the incredible story of how thousands of workers, engineers, and dreamers conquered one of the most hostile landscapes on Earth and created a modern wonder hanging in the sky. To understand why this bridge matters, we first need to understand Guizhou Province. Located in southwestern China, Guizhou is one of the most mountainous regions in the world. Endless ridges, steep cliffs, deep gorges, and isolated valleys dominate the landscape. For centuries, entire communities were separated from one another by geography. Traveling a relatively short distance often required hours of winding mountain roads or exhausting treks on foot. Even by the late 20th century, parts of the province remained disconnected from China's rapidly developing transportation network. While major cities elsewhere enjoyed highways and modern infrastructure, many people in Guizhou still faced journeys that consumed entire days. Economic development lagged behind because moving people and goods through the region was extraordinarily difficult. By the year 2000, Guizhou had virtually no modern expressway system. The challenge wasn't a lack of ambition. The challenge was the mountains themselves. As China accelerated its infrastructure expansion during the early 21st century, planners identified a critical goal: connect Guizhou to the national highway network. New roads could transform the economy, improve access to healthcare and education, and dramatically reduce travel times. However, one obstacle stood in the way of a crucial expressway route: a canyon so massive and intimidating that engineers around the world struggled to imagine a solution. The Beipan River Gorge wasn't simply deep, it was brutally deep, carved between towering cliffs that seemed designed specifically to frustrate human ambition. Roads descending into the canyon and climbing back out would be incredibly long, expensive, and dangerous. A tunnel network would face enormous geological challenges. A bridge seemed like the obvious answer, yet every conventional design repeatedly failed. Engineers weren't just fighting gravity, they were fighting nature itself. Before a single drawing could be approved, teams spent years studying the canyon. They analyzed rock formations, monitored weather patterns, measured wind speeds, and evaluated countless construction scenarios. What they discovered was alarming. Wind gusts regularly reached 140 kilometers per hour. These powerful crosswinds could destabilize equipment, threaten workers, and create dangerous vibrations within any structure built across the gorge. The canyon's extreme depth complicated every phase of construction. Traditional cranes would struggle to operate. Delivering materials would be a logistical nightmare. Even accessing the valley floor presented significant risks. Engineers knew that one mistake could trigger catastrophic consequences. For nearly 13 years, progress stalled as experts searched for a solution capable of overcoming every obstacle simultaneously. Many believed the project was simply impossible. Then came a breakthrough. In 2011, engineers finalized an innovative cable-stayed bridge design unlike anything previously attempted in the region. Rather than placing massive supports in the canyon itself, they would construct enormous towers directly on stable platforms carved into the cliff edges. These towers would support a network of high-strength steel cables capable of carrying the bridge deck across the entire gorge. On paper, the concept seemed brilliant. In reality, it would push engineering, logistics, and human endurance to their limits. Construction officially began in November 2011, and almost immediately, workers encountered their first challenge. How do you build a bridge over a canyon when reaching the bottom is nearly as difficult as climbing a mountain? The answer required courage bordering on insanity. Workers manually drilled anchor points into the canyon walls, secured ropes, and descended the cliffs using advanced climbing techniques. Temporary zip lines transported personnel and lightweight equipment across sections of the gorge. Since conventional cranes couldn't function effectively in the terrain, engineers developed custom cable transport systems capable of moving materials between the canyon's opposing sides. Before major construction could even begin, crews had to create access routes along the vertical rock faces. This required more than 200 carefully controlled blasting operations. Every explosion was followed by meticulous geological inspections. Experts examined the remaining rock for hidden fractures that might compromise the stability of future structures. Progress was painfully slow because safety demanded absolute precision. With access routes finally established, attention shifted toward constructing the foundations that would support the gigantic bridge towers. Teams worked simultaneously on both sides of the canyon. Massive drilling equipment penetrated 15 meters into solid bedrock, creating anchor systems designed to withstand unimaginable forces. There was virtually no margin for error. If the foundations failed, the entire bridge would be doomed before it even existed. Months of relentless labor followed. Workers battled difficult terrain, unpredictable weather, and constant safety risks. Eventually, after approximately 8 months, the foundation excavations were complete, yet an even greater challenge awaited. Each tower foundation required roughly 15,000 cubic meters of concrete, and that concrete had to be poured continuously without interruption. A pause during the process could create weak points or cracks, jeopardizing the structural integrity of the entire project. Inside these foundations was an incredibly dense network of reinforcing steel. The framework was so tightly packed that workers could barely move between the bars. To construct the towers themselves, engineers employed self-climbing formwork systems. These ingenious structures effectively lifted themselves higher as construction progressed, allowing crews to build upward at an astonishing pace. Tower sections rose approximately 4 meters per day. Working at such heights was extraordinarily dangerous. Strong winds constantly threatened personnel. Every platform was enclosed with extensive safety systems to reduce the risk of falls. Even experienced workers reported dizziness when looking down into the seemingly endless canyon below. Despite the hazards, construction advanced rapidly. One tower climbed 100 meters in just 62 days, setting impressive benchmarks for efficiency and precision. Accuracy was everything. After each construction stage, laser surveying equipment verified the tower's alignment. Engineers monitored deviations measured in millimeters. If a significant misalignment occurred, entire sections might need to be demolished and rebuilt. Hidden within the towers were sophisticated cable tensioning systems, designed to apply immense compressive forces to the concrete, increasing strength and stability. Computer simulations repeatedly tested the structure against earthquakes, hurricanes, and extreme weather events. The results consistently demonstrated extraordinary resilience. 18 months after construction began, 2 massive towers stood proudly on opposite sides of the canyon. Rising nearly 392 meters from their foundations, they dominated the landscape like futuristic monuments. Yet despite their size, the towers represented only half the battle. The empty space between them remained untouched. The next phase would become one of the most breathtaking spectacles in modern engineering. To support the future roadway, engineers needed to install 112 massive cables stretching between the towers and the bridge deck. These weren't ordinary steel cables. Each consisted of hundreds of individual high-strength steel wires bundled together into precisely engineered strands. Every cable would play a critical role in distributing the bridge's weight. Installation began with an operation that seemed almost cinematic. A helicopter carried a lightweight pilot line across the canyon. Flying in powerful crosswinds, the pilot had to maintain incredible precision while workers secured the line on both sides. Once completed, larger cables were gradually pulled into position. The operation resembled threading a needle while flying through a windstorm hundreds of meters above the ground. As cable installation progressed, engineers discovered an unexpected challenge. Every newly tensioned cable altered the forces acting on the others. Adjusting one cable influenced dozens more. The process resembled tuning a giant musical instrument suspended over a canyon. Tension levels had to remain within approximately 1% of their target values. Then another problem emerged. Strong winds caused certain cables to vibrate dramatically, producing eerie humming sounds. Engineers feared that prolonged oscillations could eventually lead to metal fatigue and structural damage. Working through the night, teams developed specialized dampers, essentially giant shock absorbers, installed inside the cable protection systems. Testing demonstrated remarkable success. Vibrations were dramatically reduced. Eliminating the threat, one by one, all 112 cables were completed. transforming the bridge into a magnificent steel harp hanging in the sky. With the cable system finally operational, attention turned toward the bridge deck itself. This phase required extraordinary balance. The deck couldn't simply be built from one side to the other because uneven weight distribution might destabilize the structure. Instead, construction advanced outward from both towers simultaneously. Massive prefabricated steel sections were transported to the site and lifted into place using some of the largest cranes available. Every bolt was tightened according to exact specifications and independently inspected. Welders performed delicate work hundreds of meters above the canyon floor, often battling fierce winds and difficult conditions. Day by day, the two advancing sections crept closer together. Engineers monitored every movement using sophisticated instruments capable of detecting tiny changes in position. Eventually, only a small gap remained between the approaching deck sections. Excitement grew across the project as workers anticipated the final connection. Then, a problem appeared. Detailed measurements revealed that the two ends were misaligned by approximately 3 centimeters. While that might sound insignificant, it represented a major issue at this scale. Engineers responded by carefully adjusting the tension in 12 specific cables. Over 18 painstaking hours, they gradually shifted the entire structure until the mismatch was reduced to just 2 millimeters. Finally, a massive 120-ton closure segment was lifted into position. When it settled perfectly into place, the canyon was bridged for the first time in history. Hundreds of workers simultaneously tightened final bolts according to coordinated instructions. Many later described the moment as the day the canyon disappeared. Even after construction finished, the bridge still faced its ultimate examination. More than 600 sensors embedded throughout the structure continuously monitored stress, vibration, temperature, and movement. Engineers compared this stream of information to monitoring the heartbeat of a patient. During load testing, 80 fully loaded trucks drove onto the bridge simultaneously. Everyone watched closely as the structure responded. The bridge deck deflected exactly as predicted by computer models, approximately 45 millimeters. The accuracy was astonishing. Years of calculations, simulations, and engineering decisions had been validated in a single dramatic demonstration. After 5 years of construction involving more than 3,500 workers, the bridge was officially ready to open. On December 29, 2016, the Beipanjiang Bridge welcomed its first public traffic. What had once been a grueling 5-hour journey along dangerous mountain roads was reduced to roughly 4 minutes. For local residents, the transformation was life-changing. Communities gained faster access to jobs, education, healthcare, and economic opportunities. Businesses could transport goods more efficiently. Tourism increased dramatically. Perhaps most importantly, people who had spent their entire lives isolated by geography suddenly found themselves connected to the wider world. Witnesses recalled elderly residents standing near the bridge, emotional as they watched vehicles cross a canyon that had once seemed impossible to overcome. For them, this wasn't merely a bridge. It was proof that the barriers defining generations of hardship could finally be broken. Today, the Beipanjiang Bridge stands as one of humanity's greatest engineering achievements. It is more than steel, concrete, and cables. It represents persistence in the face of overwhelming obstacles. It demonstrates what can happen when thousands of people commit themselves to solving a problem others consider impossible. Suspended high above a canyon once feared by engineers worldwide, the bridge serves as a powerful reminder that limits are often temporary. Mountains can be crossed, chasms can be bridged, and sometimes, the structures that seem impossible become the very symbols of human ingenuity. The next time you drive across an ordinary bridge, remember the Beipanjiang Bridge, a place where engineers didn't merely build a road. They conquered the sky itself,